the different properties of the energy stores, which can be more cost efficient and time efficient when done under the modeling phase and then doing real testing. You could also use the modeling for development of different control strategies. Sure that it's much more efficient to do so beforehand installation and then when everything is in place. And also it could be a good tool for making different kind of cost analysis to understand in which projects and under which conditions it can be useful to install different energy storages.
Thank you.
Yeah.
So, but however, each building, as you mentioned, is unique, and these test solutions often have a number of variable components that need to be taken into consideration, along with building and other external factors. So you have the variation of the component in the test, the variation of the building, and the variation among in the nature and like the outside factors, and thus proper modeling and integration may present a real challenge.
Yes. So as I guess all of you know as well, working with different models, it's important to find both the right quality and the right way to do the models, because it can be both kind of costly and it can be you need to spend enough time but not too much time to really make your model worthwhile for your projects. So if the purpose is to do more research on something, then you might need one quality. If it's just for an economic decision, then it's another type of a model you need. So that comes always on this type of activities, that you need to design or define and decide upon which quality and in which tools you're using. And I guess we will hear more about that when Mo and Juan Carlos will speak in a short while. Some of these trade-offs you must be know about is both when it comes to how fast or how slow your model is. That could be one reason, but also when it comes to costs. One another important factor is when it comes to how certain or uncertain your model is. What kind of conclusions can you make from the models that you have designed and used? So that's also an important factor for the ones that are using the results from the models. Yeah, so I won't go into more details. I guess we will hear much more about this when we come to these two specific cases that we will listen to. So I hand back to you, Emilia.
Thank you. And I'm actually going to pass it over to Professor Mohammed Safari, who is a lecturer and principal investigator at Dublin City University, internationally recognized for his work on sustainable buildings and integrated energy systems. His research spans from simulation, optimization, data analytics, and AI-driven methods to enhance smart buildings, multi-energy systems, and energy communities. He leads major EU and national projects, including Hystore, Norm, SEAI, and previously contributed to Ireland's SFI Energy Systems Integration Partnership Program, with expertise in thermal energy storage, demand-side flexibility, and AI ML optimization. He is a member of the APT and DCU Center for Decarbonization. Your work advances AI-enabled digital twins for flexible, low-carbon energy systems. And while we're here, and we're doing the introduction, so it'll flow, I also like to introduce Juan Carlos, who's here representing the ThumbsUp project. You are engineer and technical coordinator of the ThumbsUp project. Juan Carlos holds a degree in international engineering and a 2-year master's degree in energy generation management and efficient use from the University of Valladolid. He has over 10 years of experience in European projects, the later of which have been specifically in energy-related European projects. And you also lead the task related to building, modeling, and building energy management systems within our project. So you're going to give us, as Mohammed gives an introduction of different methodologies and what you're doing in Hystore, Juan Carlos, you're going to give the thumbs up perspective. To be noted that these two projects are funded under the same call. So we have the same goal, the same projects, but instead of competing, we've decided to collaborate in communication, but also knowledge sharing as we do here. But so we don't stay in a little bubble of researchers and EU projects as we tend to do. We are very thankful for Andreas Frana, who's here. And you're here, you have a your research innovation at Bank Dahlgren in Göteborg. He's originally from Dalarna and moved to Gothenburg in 1997 to study at Chalmers, where he got his master's and PhD in building services and engineering. Since 2017, he has worked at Bank Dahlgren Gothenburg with a long-standing involvement in the HSB Living Lab. His role has been to bridge our consultancy practice and research and development, turning ideas into practical solutions. And this is why it's so important, great that you're here with us today. He now leads their innovation work, driving both international activities and collaborative projects with external partners. So, Andreas, we look forward to getting your perspective and your questions, the discussion going. But without further ado, let's go back to Mohammed. Please tell us, like, what is the work you're doing and what's Hystore about and what's the work you're doing there?
Sure. So can I share my screen?
You should be able to.
Screen number 2 here. Okay. I assume that you can now see my screen. So first of all, thanks very much, Emilia and your team, for having me today here. I'm very delighted to meet you all here. I also appreciate again, the management team, the ThumbsUp, and also the Hystore team to organize this venue here. So I'm going to talk about the Hystore project. It will be a high-level overview of different modeling approaches we've been using in Hystore project. So I'll show you how co-simulation and optimization can help us to connect the dots between different tools that we've been using so we can take advantage of each modeling environment that is used in this energy field, especially in Hystore. So first of all, I'll show you just a few slides about our team. So as you can see that the Hystore project has 18 partners from across the European Union. Our main objectives are to reduce the capital cost of the thermal energy storage system, but also to provide and to develop actually advanced PCM-based and TCM-based thermal energy storage solutions that are compact enough and that can provide high density thermal energy and can also contribute to the grid flexibility. That is the key point in our project. So our coordinator is based in Barcelona. It's ArcBCN. And you can see also the website of the Hystore project for more information. And again, I say that the main objective in the Hystore project is to develop and validate 4 innovative sets of thermal energy storage solutions based on PCM and TCM to provide advanced solutions for domestic hot water users, space heating, and provision of hybrid services. So which means that we provide flexibility to hybrid electric thermal grids. That I will cover that also today in my presentation and some modeling efforts. We started this project in January 2023. We are aiming at technology readiness level from 4 to 7, so it's a high TRL project. We can see also a consortium here that are pushing forward beyond the boundaries of the current technology, the thermal energy storage solutions. So, but also we have 4 different pilot sites across the EU. We have a pilot in Dublin, Ireland, another pilot in Montserrat in Barcelona. We have a pilot in Langenwang in Austria and a pilot in Stockholm, which is the KTH campus. That is also, and also we are dealing with different energy systems. So some of our pilots have district heating and cooling. A pilot, for example, in Ireland only has district heating and also grid-connected buildings, etc. So we are investigating the potential of developing and installing these thermal energy storage across different climatic regions and across different pilots with different energy systems. That is very important. So to start off, I'll give a quick introduction to, again, the Hystore overall concept and that what we're trying to achieve. And after that, we'll look at the modeling approaches we've been using throughout the project. So right now, the most energy systems also that Emilia, you have mentioned that so in most energy systems, the use of thermal energy storage as a flexibility resource for electricity grid is still quite limited, and there is a real need for more research and development. That's why we are here, especially when it comes to hybrid thermal electric systems like those that combine district heating and grid-connected buildings and on-site renewable generation, for example, solar PV that we have in almost all of our pilots in Hystore projects. So Hystore is working directly in this space. The project is developing and validating 4 innovative thermal energy storage concepts using both, as I said earlier, phase change materials and thermochemical storage. So these solutions are being tested across 4 pilot sites in Ireland, Spain, Sweden, and Austria, each representing different real-world hybrid energy contexts. We are still working on these systems and in terms of installing them or validating them, and our project is still in progress. So all of this supported by a smart aggregator and an open multi-service platform, which is also another key technology in our project. So together they enable the next generation thermal energy storage solutions that can deliver advanced heating, cooling, and domestic hot water services, while also improving grid integration, flexibility, but also privacy. That is also another key topic here, and the overall sustainability of our future energy systems. These will be addressed by the Hystore project. So as we can see, the Hystore in the Hystore we develop both PCM, TCM thermal energy storage solutions, and then we'll explore the modeling, simulation, and optimization approaches utilized to develop and evaluate thermal energy storage integrated energy systems within our project. So in the next slides, we'll also walk through the key methods, software platforms. That would be great. In today's webinar, we can discuss more about that, and also the workflow strategies that enable the development, analysis, and validation of the 4 innovative thermal energy solutions deployed across the project's pilot sites in the Hystore project. Now, the core of today's presentation in terms of the modeling approaches. So in our project, but generally saying in engineering, we rely on 3 main modeling approaches: the whitebox modeling, blackbox modeling, and greybox modeling. I consider any project, any engineering project, including the thermal energy storage projects, like an art, and the engineer here is the artist. So depending on the project that we are dealing with, depending on the system that we are dealing with, we need to create separate solutions, dedicated solutions to those specific pilot sites, energy systems, and modeling exercises. So the white box models use the first principles physics to represent systems with high accuracy and interpretability. So tools such as, about it, Modelica, Open Modelica, Energy Plus, Transys, Dymola, and ANSYS rely on thermodynamics, heat transfer, and fluid mechanics or dynamics equations to reproduce real system behaviors. I'll give examples from our project in the next slide. Then we have the black box models, which are purely data-driven. Normally, we use Python, which is now widely used in our project. Then from the same environment in Python, we use machine learning, historical measurements, or simulation data that can predict system outputs without explicitly modeling physical processes. So they are really powerful for forecasting, control, and optimization when detailed system knowledge is limited, but also in parentheses, when software integration is important, for example, in our project. And then we have the greybox models. It's my favorite approach. Okay, so the greybox models combine both concepts of whitebox modeling and blackbox modeling. So they use simplified physics structures complemented with data-driven parameters, estimation, and also enabling accuracy and reduced complexity to our system. So this gray box approach is widely used in the Hystore project. I'll give you an example of our project. So I've talked about the modeling approaches. Now, in order to implement these modeling approaches of white box, black box, and gray box approaches, we need to apply the corresponding modeling methodologies within an appropriate simulation environment. Okay. Again, here is another, let's say, topic that most of engineers think about it, okay, and need to decide what to do and how to do it. So the choice of platform depends on several factors, including user expertise, project scale, license versus open source tools, software capabilities, scalability, and the ability to integrate with cloud platforms, edge devices, co-simulation, and model exchange workflows. So again, this is very important because in our project, the Hystore, we're dealing with all of this, okay, including the real-time control. So in projects such as Hystore, we routinely address all of these elements to achieve robust and interoperable modeling and simulation results. So we use a diverse set of simulation approaches to model, optimize, and evaluate thermal energy storage integrated systems. So these include physics-based modeling with Modelica, Dymola, and ANSYS, including data-driven and machine learning methods in Python. Also, we use the privacy-preserving protocols in terms of data sharing. So that is also very important. Also multi-objective optimization or hybrid optimization and FMU-based co-simulation, federated learning, and also semantic modeling through, for example, Protégé and SAREF to ensure interoperability and scalability. So I've just written here the main simulation approaches and software that we use. But today I want to talk about the white box model and then a gray box model approach that we have been using in our project. So the example here shows one of our developments. This is a PCM and heat pump model developed by our partner in AIT in Austria. So we can see a white box model of one of the Hystore PCM-based solutions. And this is a comprehensive model, which includes a physics-based model that uses thermofluid principles to represent the full energy system. Also, it integrates several sub-models or subsystems, including PCM thermal energy storage developed within our project for domestic hot water application, air source heat pump control logic, and the building space heating load profile, which comes from our pilot in Austria, and the on-site PV generation, which again comes from our pilot in Austria. But one of the challenges here is to how to optimally control this system, this heat pump and thermal energy storage, in order to contribute to grid flexibility. So the key question that arises is, how can we optimize such a system hour by hour or annually, or for example, for hour ahead and day ahead operation? Okay. Now, to address this, we have developed a co-simulation and model exchange framework using Python and FMI standard, enabling advanced optimization and control strategies to be implemented smoothly and efficiently with the detailed Modelica model, or even other Python models, or even MATLAB models. But we mainly use Modelica, Daimola, and Python within our project for the system integration. And then for the heat exchangers analysis, we use ANSYS for that work. Now, taking into account this whitebox model developed in Daimola by our team, the other question here is how to integrate it within our software environment. Okay, so to enable model exchange and co-simulation and support the integration of data-driven methods and optimization workflows, the Modelica model can be exported as an FMU, so .fmu file, which stands for the functional mockup unit. This capability is enabled by Daimola and Modelica. So this literally encapsulates the entire model and makes it straightforward to run it in other environments, such as Python. Okay, so by exporting as an FMU, the model can be also executed outside its original tool, which was Daimola, but we will use that now in another environment, including on cloud platforms or even on edge devices, which greatly expands its flexibility and deployment option. Okay, so what has been done here now is exporting the model, the whitebox model, as an FMU. And now, here I'm showing you the co-simulation and model exchange framework and architecture that we have developed within our project. We can import then our Daimola or Modelica model into Python and combine it with the powerful Python libraries on all open source tools and libraries for machine learning, for data analysis, for statistical modeling, and advanced optimization. So this significantly extends the model's capabilities and also allows us to simulate scenarios that would be difficult or even impossible to handle within a single modeling environment. So by integrating these data-driven components and machine learning models with the physics-based FMU, we effectively create a greybox model that combines and blends the first principles modeling with data-informed behavior. So with this approach, the model then can be deployed on the cloud or executed in real time, or literally on our computer, enabling more flexible and scalable applications. Again, I'm repeating that is very important, the scalability in our project and such projects. Now, a very high level explanation of the FMI. This is really very handy, very helpful in all projects, such as like Hystore project. And so we can use the FMI interface to build advanced greybox models by combining multiple specialized tools. For example, we can simulate the thermal energy storage and heat pumps in Daimola or open Modelica, and then model the building energy loads in Energy Plus, and then develop load forecasting or AI models in the Python environment. So the FMI here allows us to exchange model, and it allows us to integrate all these solutions tools into a single co-simulation and optimization environment, which in the end provides a very powerful and cross-domain analysis and control framework. So I hope I haven't.
Thank you. That was a really good explanation, at least for me, who's new to this.
Thanks very much. So I'll be happy to address any questions, to discuss more, either now or whenever you see that's suitable.
Are there any questions from the audience? Please.
Yeah, of course. So let me share the screen. So I guess you can see the screen.
Yes, thank you.
So yeah, well, first of all, I want to thank Mohammed for the presentation. I think you gave us a really clear view of the different models. And in my case, I'm gonna focus more on how we got the models and the results we obtained in the first phase of the project. So, well, as Emilia already presented the project, I just want to do like a fast overview of the project. Here, in our case, well, we have like the phase one that is focused on the development of the fragless and sortes as thermal storages for intraday cycles in the case of the fragless, and the 4-week use in the case of the sortes. Okay, here we also, we define the different applications for heating, cooling, and domestic hot water at the different system levels, and we select the most suitable modules in terms of combinations. Then in the phase two, we move to the validation side and the 3 demo buildings that already Emilia explained. And well, we in the phase 3, there is a replication campaign that we want to evaluate how easy will be for these solutions to be transferred to other buildings. So, well, first of all, here I just want to do a brief introduction of our models before starting explaining the results that we obtained. Here, for example, in the case of the fragless, as already Mohammed explained, we used Transys 18 version. Okay, in the case of in the fragless, we used MATLAB with Simulink for the development of this model. In the case of the sortes, we used Transys, the same for the building. Okay, so we developed, for example, with Google SketchUp, the structure of the buildings. Then with Transys, we developed the model. Here, I want to emphasize that it's important what we were commenting at the beginning about the validation of the models. For example, in the case of the buildings, we have to evaluate the model, and we have to consider the simulation time and the precision of the model compared to the final results. To the monitoring data, we could say. For example, in the case of 3 buildings, the Cartif 3 building in Valladolid, the single family building, and the Swedish demo in Gothenburg, we had results because there were 16 buildings. But so what we did is, okay, we have monitoring data from the past years. So we used this data to validate our models. In our case, we consider like to have hours of simulation time for a year with a precision of 4% of error in the total energy consumption. And for example, these also errors in the case of, as we will see later, we will have some thermal energy storage in a distributed mode. For example, just connected to the handling unit or the radiating floor. So we analyzed also these individual thermal installations with this threshold of validation. And then just for the integration of the frackless and sorters, we used apart from Transys, we used Python to optimize multi-objectives variables, as it's, for example, clearly, as I will explain in a minute, to maximize or to reduce the photovoltaic surplus and to minimize the energy from the grid. Okay, so after this introduction of how we developed the models and how we did the integration, I just want to start explaining like the main the control rules for this integration. So we could say that the main control rule is to prioritize the PV surplus for charging. If solar power is not sufficient, we use a night charging strategy. Then for discharging, we discharge when the building's thermal demand is high. So here on the right, for example, of this slide, we can see the diagrams that show the control logic for charging and discharging, and this optimal on-off thresholds for charging and discharging were defined using the simulation and optimization models that I explained before, developed in the first phase of the project. And well, they were adjusted for each building and season. So just to start with some results here, we can see in this slide the results of the control rules defined for the Cartif 3 building in heating and cooling modes that are the technologies that in this moment are already installed. So, for example, in the heating mode, the frackless charges whenever the PV surplus is available. For example, in this case, 1.18 kilowatt hour for the centralized and 3.36 for the kilowatt hour for the distributed one, with a night charging window between 1 to 5 a.m. During the discharge, the frackless starts when it's a higher power demand of 46 kilowatt hour for the centralized and 21 kilowatt hour for the distributed. What it means that this directly reduce the thermal demand of the heat pump. In the case of the sorters, we also charge it for during the night between 12 and 2 and discharge from 9 a.m. covering the morning demand peak. In the cooling mode, the logic is similar. Okay, so here we can see the heating simulation results for the 3 operational scenarios. So, for example, in the case 1, we had the sorters charged only with PV surplus. The case 2, the frackless plus sorters with both night and PV surplus charging. Then in the case 3, both systems with more intensive frackless operation with 4 hours at night plus PV. So here we did in this table we can see some results or an overview of the results from January, February, and March. As you can see, the results are consistent in February and March with PV surplus reductions between 8% to 18%, and with a grid reduction below 0.5%, showing a limited but a positive energy impact. So the conclusions here are that the main benefit lies in a better PV cell consumption and the peak demand reduction of the heat pump. Here we have the cooling simulations for the Cartif during July and August, comparing the baseline, integrating the frackless and sorters individually and combined. And the results show that the grid consumption remains close to baseline, but the same than before, with a PV utilization that increased notably, we could say, and the building electrical peak is reduced during the local cooling load hours. So in the cooling season, we could say the impact is mainly operational. We could say that the storage shifts part from the heat pump consumption to periods where the PV generation is high. So it improves the match between supply and demand. That clearly this is what we are looking for with the thermal energy storage. So here, for example, we can see just an example of the integration for charging and discharging cycles of the thermal energy storage systems in Cartif. That here we combine both the scheduled night charging and the PV charge mode. Here we could say that we ensure the energy availability during the demand peaks, and we reduce directly the heat pump electricity consumption. For example, in the red line that indicates the state of charge of the sorters, we can see how every day during these hours is charged. Then, for example, with the green and blue lines that correspond to the distributed and centralized frackless. And then, for example, there you can see the yellow line that shows the PV surplus, and the PV, in this case, the purple line that is the heater power for the frackless. Now, let's continue with the Veolia single family building. So here, as you can see, there is like a frackless dedicated to the domestic hot water and sorters, supporting heating and cooling. For the case one, for the frackless, only with the frackless, the building consumption increased by 18 kilowatt hours, but using 209 kilowatt hour of PV surplus. The case two, that is the frackless plus the sorters with the night charging. Here there is a higher building consumption with the similar PV use. So clearly this use case is less beneficial. And the case three, that both PV charged, that we can see here that the PV surplus drops like around 900 kilowatt hour, and the building consumption increased by 624. So in summary, here it's important the coordination between the frackless and the sorters to cover all the solar energy surplus and the off-peak energy. And with these results, we obtained around two charge-discharge cycles per month for the frackless, and 3-4 for the sorters. And here we can see the control rules for the multifamily building. Here we have integrated one that centralized, distributed, and domestic hot water frackless. As you can see, the rules were optimized with the models that I commented about with Transys and Python, and we could say that the centralized buffer the heat pump in this building. The distributed smooth, we could say, the radiant floor, and in the case of the domestic water, supports the system during the summer operation. Here we can see the results of in these three cases. For example, in the centralized, we increased we reduced in some kilowatt hour the heat pump electricity consumption, but in this building the boiler decreased by 4.1%. So what it means, at the end of the day, we use less fuel consumption. In the case of the distributed, the heat pump decreased slightly from -40 to -60. That is at least some beneficial. Then, here the main benefit, the main benefit is the peak saving, because we could reduce the demand spike in the radiating floor, providing some flexibility. And in the case of the domestic water, the energy effect is very low, around 0.5%, but clearly it helps to stabilize the heat pump operation. And here we have the last demo, that are the control rules defined for the 3D demo in Göteborg, for the centralized and the distributed that are being installed right now. So the main control objectives are focused to reduce the district heating network energy use, and to flatten the electrical load profile. So here we can see the results obtained in the simulation and optimization. For example, for the heat pump electricity consumption in the distributed frackless, we reduced by about 78 kilowatt hour per month. So then the district heating network, we reduced around 179, plus the consumption of the auxiliary heater, give us like a net positive electrical balance of 44 kilowatt hour per month. So what it means that at the end of the day, this gives us some efficient operation. And for the case of the domestic water, we reduced around 10 kilowatt hour per month. In this case, there is no auxiliary heater. And we also reduced the district heating network around 140 kilowatt hour per month. So in both cases, what it gives us is some like successful, we would say, successful reduction of the district heating network energy use. We smooth the electrical demand profile, and at the end of the day, we obtain a balanced operation, and we increase the renewable self-consumption.
Thank you.
That's it from my side. If you have any question.